Thanks for the organizers for invitation. It's very a pleasure to be here and to see so many Japanese colleagues also, which reminds me some good time in Numazu. So I'm happy to give this talk here. So the topic of my talk is a differential equation for Reidemeister torsion. So I apologize for those who already hear me talking about that many times because it's kind of old subject. I've not been thinking about that for some years now, but I found that it really fitted the topic of the conference. So it's really about character varieties and quantum invariants, and so I decided to talk about that topic I like very much. Although it's quite, I've not many new things to say about it, but I hope you will be interested in it. So indeed, I will not. This is some word I will not really get into this question about Reidemeister torsion because it's it's very interesting but quite technical, and I decided to say something around the question, but you will not see a definition of Reidemeister torsion in my talk. So my plan is to give two parts. So the first part will be about character varieties. This will be the main theme, but the tool I would like to explain is some object which is called the first order Kaufman bracket. So I will spend some time explaining what it is and why I believe it's important for this question. And the second part will be about asymptotics of quantum invariants. And it is indeed the motivation for the first part. So be patient if you don't understand why I'm interested in the first part. And the tool I would like, I hope that I will have time to explain, is some object I want to explain is the twisted self-linking number. Twisted self-linking. Okay, so I will try to explain how it fits in this kind of questions. So let me start with some motivation from character varieties. So I would like to start from typical three-manifold. So say M, a closed, oriented, connected three-manifold. I would like to say something about it. Well, the most generic three-manifold I have in mind. So generically, it should be hyperbolic as a first guess. So suppose it's hyperbolic. So what does it mean? It means that M is the quotient of H3 of the hyperbolic space by some subgroup of the set of isometries. In particular, it has a representation in obviously fundamental group into the group of isometries of the hyperbolic space. So there is a very important representation from pi1 of M to the group of isometry of H3, the 3 space, hyperbolic 3 space, which preserves orientation. So this group is easy to, well, it's well known that it's the group PSL2 of C. And I would like to remove this P here, so I use some well-known fact. I claim, well, it's a result by Thurston, a simple one, that indeed you can lift this representation to SL2C. So there is a favorite representation rho tilde from pi1 of M to SL2C, which is faithful and discrete. And I would like to say just something more about this representation. It's rigid in some sense. So this is a well-known rigidity result. which is due to maybe Calabi, Veil, and you can even add Mostow. Well, there are a lot of people, but let me give just 3 names. What does it say? It says that if you have a continuous family of representation of pi1 of m into the same group SL2C, all these representations are the same. So let me be more precise. If rho t is a continuous family of representations, then there exists a continuous family of elements in SL2C such that rho t is equal to rho 0 is equal to rho tilde. So if you deform this representation rho tilde, then you do not really deform it. So rho t is gt rho tilde gt inverse. So that's okay. So this is the third one. So I have a strange order in my blackboard. So we had a discussion last night. That's why I decided to do exactly like that. And, oh no, the third one. Okay, is that okay? So in order to identify this is a conjugation equivalence. So I would like to say that these two representations are indeed the same. So there is a useful trick to define this character variety. So let me recall how it is defined. So in order to quotient by conjugation, we introduce something which is slightly more complicated than just the quotient by conjugation. Is a character variety. So the character variety of M, by definition, it will be the set of all representations from pi1 of M to SL2C, divided by some relation which is not precisely conjugation, but something stranger. The conjugation is that rho is equivalent to rho prime if and only if they have the same traces. For any element of pi1 of M, trace of rho of gamma is equal to trace of rho prime of gamma. Okay, so that's exactly the quotient we have in mind. So why do we do that? So there are many reasons. The main reason is that quotient makes X of M as something more than just a topological space. It's an affine algebraic variety. So X of M is an affine algebraic variety. And if you look at this quotient here, you see that the trace function T gamma is a map from X of M to C, which maps a representation rho to the trace of rho of gamma is well defined. And indeed, the quotient is just made so that it's well defined, and just these maps are well defined. So indeed, these functions have a particular role. They are regular functions. They are algebraic functions on the character varieties. And we can say much more than that. Indeed, we can prove that. So I didn't really define the right way X of M. I made a quick definition, so I cannot really write a theorem here. But indeed, the ring of regular functions on X of M is exactly generated by these trace functions. So any regular function is indeed a polynomial in trace function. So it's the polynomial algebra generated by all these elements here. So here, imagine I make a kind of formal polynomial algebra given by all these T gammas for any gamma in pi1 of M. This is obviously too big. This is not finitely generated, but it's an algebra, and I can quotient it by an ideal, which I explicitly give by some relations. And we know exactly which relation we have to add here. So the first one is if you take the trivial element T1, the trace of the identity should be equal to 2. So T1 minus 2. And the other one is the famous relation which holds for given 2 by 2 matrices, which is the following one: T gamma delta plus T gamma delta inverse is equal to T gamma and T delta. Okay, so this is called the SL2 trace relation. And it's extremely important in my talk. So I really stress that this is the only relation, well, this one of course, you have to add in order to define the structure of algebraic variety. And this theorem is indeed very old. Well, it's a strange story. The credits for this theorem are very difficult to give. So maybe it should start with Fricke. So Fricke was a student of Klein. So it was maybe 1890. So it's very, very old kind of result. It's part of invariant, what we call invariant theory. Of course, it was not completely proved by Fricke, but many questions was addressed in his work. And you can find a lot of people here. So maybe I can add Magnus, who did some work about that. Other people, maybe the most important, I would say, who really gave the modern proof is Procesi. In some paper in just make permutation of some, and other people are still, like me, rediscovering it at some point. So it's difficult to find one's way in this kind of questions. Okay, so I take this for granted, and let me make some other comment about that. So suppose that I start from a representation. I really want to say something more about this equivalence relation. So suppose that you have irreducible representations, that the row from pi1 of m to SL2C is irreducible. So for instance, the geometric representation is irreducible. So in that case, I would like to say more about this equivalence class. So it's well known that another representation, rho prime, will be equivalent to rho if and only if it's conjugated. So it's some trick, not very difficult to prove by hand. If and only if rho prime is equal to G rho G inverse for some G. Okay, so in that case, the conjugation is exactly the same as a trace equivalence. And let me say something more about, moreover, another theorem which is hard to follow, but maybe let me say it's due to Weil. We can really describe exactly what the infinitesimal neighborhood of this representation. So the tangent space, so if rho is irreducible, still, then we can, in some sense, compute the Zariski tangent space of the character variety. So recall that this is an algebraic variety. In no way it is smooth, but it's an algebraic variety. So it has some tangent space. It's well defined. So it's Zariski, but usually I do not write Zariski here. And this can be computed, well, it can be computed differently, just say, with some H1 here of the variety M with coefficient in some twisted coefficients, add rho. So what is add rho? It's just a representation from pi1 of M to SL2C, which is given by conjugation from acting on SL2C by conjugation. Okay, this is an adjoint representation. So gamma acting on psi is rho of gamma psi, rho of gamma inverse. So I don't want to give the precise definition of this H1, but I will use it many times as a kind of notation for this tangent space. And I just say that the proof of the rigidity result by, where it is, okay, it's hidden, is exactly a computation of H1. So at some point, the proof of Calabi-Weil is that H1 of M with coefficient in A, the row tilde is equal to 0. This is exactly how we prove rigidity in some sense. Implies a rigidity result. Okay? So let me try to find a no questions for now?
You see again, what is the last point about rho theta?
The last? What is the last point?
What you said about rho tilde?
Yes.
What is it? Rho tilde is the lift to SL2C or something else?
Yes, it's the lift of the hyperbolic representation to SL2C. One lift. Indeed, there can be more.
But before, to define adjoint of rho, here rho was going to PSL2C, or it was also?
You could define ad rho with a PSL2C representation, but first I lift it. It's possible.
So here is the general definition of ad rho, and here for rho tilde, it's in the case of the hyperbolic manifold.
Yes. Rho tilde is the lift of the hyperbolic manifold. So let me try to explain the same story, or maybe quicker, using the point of view of skin module. So what is the skin module point of view here? So I have to recall you, I hope that you already heard about it, because it's this Kaufman bracket skin module. So there is a purely topological point of view for defining this character variety. And this is this Kaufman module. So let me recall how it is defined. So let M be any closed, not any compact oriented connected manifold. But maybe with boundary. Then I defined the Kaufman skin module as I will denote it by S, like S skin module of M. It's a free, let us consider the free module generated by over this ring of polynomials in A and A inverse. Free module generated by links. Banded links. So by banded links, I mean embedding of annuli. So S1 times 0, 1 embedded in the manifold, divided by some local relation up to two local relations. So the first one, Kaufman 1, the following one. So once you find a crossing in the ball, you can replace it by something like that or something like that. This is the first Kaufman rule, and the second one. If you find a trivial knot in some link, you can remove it, and the result gets multiplied by minus A2 minus A minus 2, and you remove the trivial knot, and this is the second relation. So this is a well-known module, and we don't know many things about it, indeed. But at least one thing is known, is that the first example, here I use a kind of general module. A is a kind of formal variable. But in all my cases, I will take as A some specific element. So the first example is if you take A of M equal to -1, so I mean you do this tensor product here, it doesn't just mean that you take A equal to -1, okay? So this is, let us this, I will call it the Kaufman algebra at -1. Okay, so just the definition of S of M. And this is a commutative algebra. The product is just given by disjoint union. If you have two links in M, you just take disjoint union and suppose that they are disjoint, and it's well defined. And this is an algebra we already saw. Okay, it's exactly the same algebra as the algebra of trace functions. So that's easy to prove indeed once you know what is the algebra of trace functions. And so this is disjoint union. And the point is that S of M is isomorphic to this algebra of regular functions on the character variety. And the way it is related is that the trace function T gamma, so there is a small trick here, is the same as minus gamma. So there is a small sign everywhere, but not very important. Okay, so it's exactly the algebra of functions on the character variety. So what do we expect for a typical manifold? So I should have said that before.
What's the framing?
Sorry?
What's the framing for your gamma?
Just because you put A equal to -1, we doesn't care. We do not care.
Oh, okay.
Okay? Because if you add framing, this is minus A cubed times that. Okay? In general. So A equal to -1 just gives you that you don't care. Okay? That's why you cannot put anything else than -1 indeed here. For a typical three manifold, so, well, I should have said that before, but I told you that a typical three manifold is hyperbolic, so there is a favorite representation in SL2C which is rigid. I claim that, well, I do not have a proof of it, but if you take a generic three manifold, we have a finite number of representations. All of them are rigid. Okay? So that's a kind of guess. I do not have a precise statement for it because I do not have a definition of a typical three manifold. So for a typical three manifold, we expect all representations rho from pi1 of M to SL2C to be rigid. So what does it mean? It means that X of M, well, it's a collection of points, and all these points are isolated. So what in algebraic geometry we say it's reduced of dimension 0. So there is some trick here. I do not want to get into that problem, but in algebraic geometry, a point can be a double point or a triple point. And we do not expect that in general. Okay? So what does it mean? It's exactly equivalent to say that for any row, say irreducible one, I would like to, problem of the trivial representation, I would like to skip it. Irreducible, H1 of M and add row is 0.
Here you assume that you have no boundary.
Yes, yes. Yes, thank you. So I have another way to say, I have another equivalence here. So this the same can be formulated in terms of skin module indeed. So what is the algebra of function on the finite set of points? It's just the algebra C to the n. Okay, it's a very simple algebra. So it's the same as saying that S of M is just this algebra. Okay, so this is really the kind of thing I expect, but again, I do not have any, well, I have some partial results for claiming that, but I don't know in general. But I will assume it in a while. So what the main object here is this, I really can come to the definition, is this first order skin module. So what does it mean? Well, I said if A is equal to -1, what you get is a very nice algebra, which we completely understand in a topological point of view. It's algebra of, corresponding to the character variety. So I would like to take A equal to -1 plus some very small thing. Okay, so that's the first order thing. So the definition is S prime of M. So prime like a derivation or first order is you take the same thing here, but now you take something just little more than C. So C epsilon divided by epsilon square, okay? So it's very usual in algebraic geometry, the tangent, the way to define tangent vectors. And you take A equal to -1 plus epsilon. Okay? So that's the thing I want to study here. So this is a first order Kaufman module. So the first point is that, so this is not an algebra. Okay? So it's not an algebra of functions or something, it's something more, there is less structure, it's just a module. But it's a module over a C of epsilon and epsilon square. But let me say something about the relation with S prime of M and S of M. At least I can write a kind of diagram, which is easy. So if you take epsilon equal to 0, if you just divide by epsilon, well, you get back something in S of M. And this is a surjective, quite obvious here. And inside here, if you just want to describe or to try to describe the kernel of this map, you can just multiply by epsilon. So if you start here from S of M and you multiply by epsilon, clearly the composition here is 0. Okay? So I just claim that it's almost obvious that this is a complex. Okay? I almost said that it's an exact sequence, and finally I didn't. Okay? So I believe it's exact in general, but I have no proof. Okay? So first question. For any manifold, I have no examples where it's not exact. Well, it's easy to prove that it's a surjective, but that's all what I'm able to prove. Okay? So I will show you why I care about that. And there is some very important example an important example where I can prove it's exact, but I can prove more. Is a case where M is the product of a surface with 0, 1. Because in that case, if you have a link inside a surface cross 0, 1, and you have another one, you can just put first link above the other. So this is a well-defined structure of algebra on that. So in that case, so there are many things. So first, SA of M. So at first I should say that SA of M is free and generated by what we call multi-curves. A multi-curve is just a disjoint union of simple curves which do not intersect. So this is easy to prove. If you have a link inside sigma cross an interval, if you see a crossing, you can just apply this relation, and you remove one crossing and then another one, and at the end you have just a collection of simple curves, and they are independent in the module. So it's easy to prove that it's a free module. So in particular, this implies that the derived module here is, because you have a favorite basis, you have a kind of isomorphism here between this and this, an isomorphism of modules over this ring. This is just because there is a geometric basis, so you can identify the basis here with the basis there and take coefficients. So this is a simple thing to do. But what I claim is that here I have an algebra structure. So this is an algebra, a non-commutative algebra. S of M is an algebra, and this is an algebra. So on the left you have a non-commutative algebra, and on the right you have a commutative one. Okay, and they are isomorphic as modules. So it tells you that there is some trick here. So the two products are not compatible in some sense. I can write a formula. So if I start from elements here in that point of view, I can write it as f plus epsilon times f prime. Okay, so just 0 order and first order. And I multiply them. Then I multiply them in this algebra here. And you can do the computation, you find, well, it's not easy, huh? It's something. So you find something which is natural, is fg plus epsilon fg prime plus f prime g, which is the algebra structure on the here. But you have to add some extra thing here, which makes it non-commutative. And this, I don't want to get too much inside the definition of it. It's a famous Poisson bracket. So this is a Poisson bracket associated to the symplectic structure on X of M. So this is a very important fact, which I do not have time to explain, but this is mainly due to Atiyah, Bott, and then Goldman, is that for any closed surface, the character variety of the surface is indeed a symplectic variety. There is a natural symplectic structure, which is equivalent to this, how do we say? J'ai oublié le terme. Well, is a symplectic manifold. Well, I forgot. So what we see from that example is that this Kaufmann, this derived module is related to the symplectic structure in the case of surface. But I'm interested in the case of three manifold. And there is much less information in this module, because it's where you just have a module, you don't have an algebra. And this is really the kind of the starting point from the question I'm interested in. So what happens? So it's hard to say anything in the case of a manifold without boundary, because we just have a module, and there is not much to say about the structure of this module. The interesting case is the case when you have a manifold with non-trivial boundary. Okay, so what happens if M is a manifold with boundary? So let me say something about algebraic geometry. A simple thing is that a simple fact, if you have a map F, an algebraic map between two algebraic varieties, affine algebraic varieties, to give this map is the same as to give a map from the algebra of functions here to the algebra of functions there. So it's equivalent in some sense to give some map from the algebra of functions of y to the algebra of functions of y given by precomposition. Okay, so this is the way we define algebraic functions indeed. So here, if you look at the kernel of this map of algebra, so if you look at the ideal defining by the kernel of F star is an ideal in here, and an ideal corresponds to a subvariety of y. Okay, so it defines it's an ideal of function which vanishes on some subvariety of y, and which subvariety it is. It's the image of the map, indeed the Zariski closure of the image. So the fact, which I just assume to be true, it's a very basic of algebraic geometry, is that the kernel of F star defines the closure of f of x. Okay, so it's almost a definition in some sense. So let me give a main example I'm interested in. Well, I'm considering a manifold M with boundary. So I have the skin module of the boundary, or say boundary of M times 0, 1. So I take a tubular neighborhood of the boundary of M. This is a skin module here. And I look at the at the inclusion map to S of M. This is just given by inclusion. If I have a link close to the boundary, I can just consider the same link inside M. And the kernel of this, so I define P to be the kernel. And I can give now the interpretation of this ideal here. So the interpretation, well, you have the character variety of M, a representation of the pi1 of M. You can just restrict it to the boundary. Look at the restriction of this representation to the boundary. It's, I call it res. It's rho restricted to the pi1 of the boundary of M. This is a natural algebraic map. And P is just, P defines the image of the restriction of X of M inside the character variety of the boundary. So just the restriction, the image of the restriction map. So let me try to explain, to go further. I'm quite slow, unfortunately. So what happens? So this is very classical. All this could have been defined without skin modules. This is just a thing about character variety. So now I really want to do the case of the derived skin. So what happens for derived or first order skin modules? Well, you have this natural map, this inclusion map. It's defined for prime or not prime for every skin module. So you have indeed this. I can write a kind of big diagram. You have the boundary of M, and you have the inclusion map into M. This is a well-defined map here. And I define P prime to be the kernel of this map, okay? And now I can play with the other sequence here, okay? I can make a big diagram. I put this in vertical rows. So I have this thing here. S of M, S of M, S of boundary of M, S of boundary of M, 0, 0, 0. And here I have P, P. So can you read my diagram? Okay, so I just put everything in order. And I claim that in these diagrams there are some things which are interesting and related to this symplectic structure, etc. So let me just assume, to explain that to you, assume that, for instance, all the rows are exact. That's a funny assumption, because indeed you can prove that this is exact because this is just a surface, and I claim that for the case of surface it's exact. And if this is exact, indeed, it's almost the same as this is exact because you have snake lemmas and homological algebra. So it's kind of natural to assume that, okay? And let me show that. Let me write this equation, P, P, two elements in the kernel, if you take the Kaufman bracket, belongs to P. What does it mean? It means that P is a Lagrangian ideal. And why do I care? I just care that, what does it mean that P is a Lagrangian ideal? It means that here, the image of this map is Lagrangian with respect to the symplectic structure, which is something we really care about. And here I can give you a kind of skin proof of it. And I just use diagram chase. Okay, so it's very easy to prove once you assume just exactness here. So let me make the proof here. It's very short. So you take two elements in P, say F and G. I want to prove that their Kaufman bracket is in P. Okay? So I first use the fact that here it's surjective. Okay? So it means that once I have F, I can find F prime such that F plus epsilon F primes is in P prime. And for any G in P, I can find a G prime such that G plus epsilon G prime is in P prime. But P prime is the kernel of this here, and this is an algebra, and P prime is an ideal, okay, in this algebra. It means that if I look at the commutator here of these two, this is in P prime. Just because P prime is an ideal, it's stable by multiplication. And if you use this algebra structure here and you compute the commutator, what you find is exactly, make the computation here, it's epsilon times Fg. Okay? You have to do the computation, but it's a trivial one. So this commutator here is in P prime, but it's epsilon times somebody here in P. Okay? So if I assume that this map is injective, this exactly means that Fg is in P. So I used almost everything about this assumption to prove that you have a Lagrangian ideal here. So let me now tell you the general question I'm asking.
Julien?
Yes?
Your assumption that all rows were exact, but were they the verticals?
Columns. I always interchange rows and columns, I'm sorry. Columns. So let me try to extract from this the main question, which is the title of my topic. The thing I really wanted to prove, and I spent some years thinking about it, and finally I gave up. So indeed, the main question I'm interested in is the following. So again, take this diagram here and start from F in P. Take F in P. Well, the assumption of surjectivity tells you that there is a F prime such that there exists F prime such that F plus epsilon F prime is in P prime. Okay? And if you think about it, F prime is well defined up to some specific element which is in P. And F prime is well defined up to an element of P. So what it means that there is a well-defined map from P to, let me write it, so the map which sends F to F prime is a well-defined map from P to the algebra of functions of sigma divided by P. Okay? And see, you can think about it, this is the ideal of function which vanish on the restriction of the character variety, and this is the algebra of functions on the restriction of the character variety. So this should have a kind of geometric explanation, and this if it is well defined. So let me call it U of F, and the main question is that I have an explicit formula for it. I am not able to prove in general, so the main question is to prove that U of F is given by something explicit, -2 times, so it looks ugly formula, but I like it a lot. The divergence of x of f, so divergence is not completely well defined, so I put a t here. So x of f, what is x of f? It's a Hamiltonian vector field, it's a symplectic gradient. If you have a function on a symplectic variety, you have a gradient, relatively to the symplectic structure. So this is symplectic gradient. And the divergence, maybe you know that in a manifold, there is no well-defined divergence. It's relative to a volume form. It's indeed the derivative of the volume form. And the volume form which is here hidden is a Reidemeister torsion. So here I do not get into that problem. But you have another way to define it, minus L. It's a logarithmic derivative of the Reidemeister torsion. I just claimed that there is a natural volume form on the character variety, Reidemeister torsion. And if you take the derivative of it, you should get this U of F here. Okay? And if you write down, maybe you know from vectorial calculus that the divergence of the gradient is, do you remember? Laplacian, okay? The divergence of gradient of a function, if you take the usual formula, it's a Laplacian. Here I do not take the usual gradient, but it's a kind of a symplectic Laplacian of f. If you write down formula, it's really a sum of d2f over dxy dy of y, where x and y are Darboux coordinates. Okay, so d, such that the formula here is omega is a sum of dxi which dy, if you really want to write a formula, an explicit formula here. So that's the main question I'm really interested in. So I could prove it for some specific examples. So proved for figure 8 knot, for instance. And for more for handle bodies. So this is a blind computation. I know everything, I just compute everything, and I find that A is equal to B. I don't understand anything in that proof, okay? And I really don't suggest anybody to do the same for other knots. It's just horrible. But a better proof is for handle bodies, okay? But still, it's not easy to prove, okay? So even for a very simple three manifold like a handle body, it takes me 2 pages of computations. Okay. So let me, I don't know how much time I have left, quarter of hour. So let me try to talk about motivations. Because maybe you don't see it, but it really comes from questions about asymptotics of quantum invariance. So let me try to say some words about it. So if you're completely lost, you can get back to the it's really something different. So how much time do I have? Just a quarter? Yes, ma'am. The motivations from asymptotics of quantum invariance. So the main question is really related to this Witten conjecture. So this Witten conjecture is about this invariant zk of m. Let me add some link here to be more general. So this is a Witten Reshetikhin to Rayev invariant of level k and gauge group SU2. And M is a closed manifold, and L is a link, a banded link inside M. So there is a formula due to Witten, which is a path integral. And there is a real computable formula due to Reshetikhin to Rayev to give the precise meaning of it. But let me explain. Let me give the formula by Witten. It is this path integral which really gives the motivation for what I'm talking about. So zk of m and l is a big, not rigorous integral here. So e to the ak Chern-Simons of a and here trace of holonomy L of A. So I should put a minus, okay, to be, but I will remove it just not to save some time, okay? Times dA, okay? So this, well, the only thing which doesn't make sense in this formula is this, okay? Everything else is completely rigorous, and you can really make computations. So this A, you can think of it just as a one form on M with values in SU2. SU2 is the Lie algebra of the group SU2. This Chern-Simons of A is some explicit integral formula, which can be computed, but I don't want to give the formula here. And holonomy of A is just the holonomy of this one form, so it's the integration of A in some non-commutative sense. And the trace is the trace. So this, well, some part of this equation makes sense, okay? And if you really believe here the equality, it gives you the Witten conjecture. Is the behavior of this invariant when k goes to infinity. Because you can expect some phase approximation, stationary phase, and the critical point of the Chern-Simons functions are flat connections, so it corresponds to representations. So the character variety comes here, okay, by one of them into SU2. So the Witten conjecture tells the following: that k of m is equal to the sum of representation of pi1 of m to SU2 up to conjugation. And here you have some phase, Chern-Simons of rho. So rho will correspond to A, to the flat connection A. There is some phase, I'm saving time, okay? There is some 8th root of unity I don't put here. And you have the Reidemeister torsion, which comes here. And here, maybe it's a case of what happens if you don't put a link here. So you have to remind that there is a link somewhere. So if there is a link somewhere, it's not inside the phase. So if you are used to the stationary phase approximation, it gets just multiplication in the asymptotics. Okay, it's not inside the phase. So it just here I just multiply by trace of rho of L. Okay, this is what we expect from the analysis. So this is the usual Witten conjecture, but there are many variants, and here it's not an equality, it's an equality up to O of 1 over k. Okay, it's just first order in the asymptotics. But you can try to expand it in powers of 1 over k. You can try to find the complete expansion of it. And that's really where this comes from. So if you try to take powers of k, well, you have this thing which is oscillating, and you have expansion of 1 over k, but you can hope to factorize them like this. So you have a sum of representations, and then an expansion inside each factor. And here, let me write it I pi over k times phi rho of L. And here, I can put a 1 over k squared because I already have 1 over k here. Okay, so I just add one more term. So this is completely conjectural. Huh? This Witten formula is still a conjecture, and this new one is more a conjecture. Okay, so but it's quite we can believe it, and the main point here is that it's an observation by Witten. So the main observation, one of the main observations by Witten from which makes this integral computable is that it satisfies this Kaufmann relation. It means that the map which maps L to zk of m and L satisfies this Kaufmann 1 and Kaufmann 2. So the proof of Witten I don't understand, but something. I did not define it. It's some expression which depends on rho and L. Okay, but it should be some number. Okay, So this integral, unless it is not well defined, it should satisfy the Kaufman relations for A equal to minus I pi over 2k. Don't ask me why, I don't understand, but this is really the starting point from the rigorous definition of the Witten invariant. Okay? So this means that you have a well-defined map from SA of M. So I can again change coefficient instead of taking -1 or -1 plus epsilon, I can do something different. Minus I pi divided by 2k to C. And this is a map which maps L to zk of M and L. And it satisfies the Kaufman relations because we believe it. So what does it mean for us? This implies, if we believe it, that, well, if you take A equal minus I pi over 2k and you take an expansion when k goes to infinity, what you find is that A is equal to -1 plus epsilon, epsilon being equal to I pi divided by 2k. Okay, so this exactly says that, at least in a heuristical level, that the map from S prime of M to C times epsilon divided by epsilon square, which maps L to trace of rho of L. So here I put back the minus, which should be here, plus epsilon times phi rho of L, is well defined. Just because, if the expansion makes sense, if the expansion is true, because this invariant satisfies the Kaufman relation, if you take an expansion, it should satisfy the Kaufman relation at epsilon, like that, okay? So the question is, now, what is this phi rho? I can now answer the question. So how to define phi rho of L? Because before proving the Witten expansion, you should at least define the terms which are inside, okay? And indeed, this is completely related to the first question about the derived or the first order skin module. You should prove. So if this phi rho is well defined, so this is just a remark. If phi rho is well defined for every row, this implies indeed that the sequence, the complex I was giving at the beginning is indeed exact. This implies that S prime of M is isomorphic to Sm tensor C epsilon divided by epsilon square. So you really have this regularity assumption, etc. It's completely related to that. And the thing I wanted to say, but now I have just 2 minutes, is that I have at least a definition of it. And this is this twisted self-linking number. So maybe I gave 3 talks on that topics, and at every time I couldn't define the twisted self-linking number. So that's a pity, but let me just say one word about it. It's defined. So the trick is to add twisted coefficients, which makes the thing complicated to explain. I cannot say it in 2 minutes. But indeed, I like to say the following trick. What is the laziest way to define the linking number of 2 knots in R3? If you really don't want to prove anything, I have my favorite one is to consider. So imagine you have L and L prime, 2 knots, disjoint knots in R3. So I can consider the configuration space of 2 points in R3. Okay? And inside this configuration space, I have considered the space of 2 points, one in L and one in L prime. Okay? So inside I have the class of L times L prime, which is a 2 torus. Okay, if I take 1 point in L and 1 point in L prime, this gives me a cycle, a 2 cycle in the configuration space of 2 points in R3. So this is an element of H2 of C2 of R3. Okay, it's just a kind of trivial cycle. And if you do a computation of that, you will find that this is Z. Because you take 2 points in R3, you can just consider the vector which joins the first point to the second and normalize it. It's a sphere, S2. Okay? It's homotopic to a sphere, so this group is Z, and the class of L cross L prime is just its linking number. So this is a kind of trivial way to define the linking number. And if you replace R3 by M, and you add here some crazy coefficients, you will have the definition of the twisted linking number. Okay? I cannot say more, I'm sorry. So let me stop here.
So, any question or comment?
What's the relation between phi rho and your? Oh, sorry. So, what's the relation between phi rho and your crazy Laplacian one you defined before? Expecting relation, I guess.
No, there is no relation, because indeed there are two somewhat independent questions. The case of a manifold with boundary, where the question I ask is this question about crazy the symplectic Laplacian, and there is another this question about open varieties. I'm more interested in it, but I do not know how to prove anything. And there is the other question about closed three-manifold, which is a definition of this phi rho. And this I have something to say, so that's why I prefer to talk about the second topic. But these two are not completely, well, I believe there are relations, but I'm not able to, I don't exactly know which one. So I think there is still some work to do here.
Other question or comment?
You think there is a chance to extract this phi rho from basically to IF at the big order root of unity?
Yes.
Yeah.
Well, I believe this generalized Witten conjecture should be true.
But you would like independent definition.
Yes. This is what I said. Before proving the Witten conjecture, you have to define the terms which are inside.
Yeah.
So this is something I used to say about Witten conjecture. For instance, in order for this conjecture to make sense, even if you don't put any link inside, you should have a sum here of representation where the torsion is well defined everywhere. This is not automatic. There are many examples where you cannot. So first define all terms, and the only term which is not defined for the moment was this phi rho. So here is I have a kind of definition, and then the work is to prove the Witten conjecture, which is a much more complicated problem. I don't know if I answered your question. Of course, you could define phi rho as a first order term in the Witten expansion. But first you should have to prove that there is such an expansion, and then it doesn't give you any information. So. Indeed, I have another interpretation of phi rho. Maybe you will prefer it, but it's not really... well, when you do a stationary phase, there are formulas, explicit formulas for all the terms, which are from analysis. Okay? And indeed, phi rho can be defined in the following way. If you really believe in path integrals, you take the second derivative of the trace function on the space of all connections, and you contract it with the quadratic term of the Chern-Simons function, which is a kind of, so you can make a kind of analytic definition of phi rho as a constructed from the second derivative of the trace function, but maybe it's not what you want to hear.
I mean, you have some universal formula for this specific to IF, at least from homology spheres.
Yes.
And so here there are expansions. We believe that
Yes.
we will recover the coefficient.
Yes, that's what I expect.
And what about the role of the flat connection here? This expansion in arithmetic area is supposed to be for the trivial connection. So that's the flat connection plays.
So maybe we're not talking about exactly the same. No, really, written conjecture says that the k of m, even if you remove L, this quantum invariant, the written logistic invariant, should have an expansion which is the sum over all representations, not only the trivial one.
You do not separate those.
And I try to isolate any contribution of any representation in the formula. That's what I try to do. But it's clear that if you do some specific expansion, you just get the contribution of the trivial representation. But this is not what I'm doing here.
This is what that was my question.
Other question or comment?
It might be just a technical thing, but at one point you passed from SL2C to SU2C, SU2.
Yes.
And so your phi of rho, here it's rho is a representation into SU2. And
well, I tried.
Do you just take
try to escape from that, but that's a strange thing. Is that of course everything is well defined in the realm of algebraic geometry. Everything is defined over SL to C. That's where everything makes sense. But for some reason, in this sum, we expect just SU2 representations. In that sum here, so there are many representations which are not in SU2. Which disappear. So maybe they are exponentially small. I don't know, okay? But for the definitions here of phi rho, of whatever, twisted Deakin numbers, anything you can define from algebraic topology doesn't make any difference if it's in SU2, SL2C. So there is a general definition, and you can just plug your favorite representation. So maybe the hyperbolic one, which is definitely not in SU2, or representation in SU2. It gives you formulas. So I'm cheating a little here for phi rho to make sense. I need something more than just irreducible. It's better if the representation is Zariski dense. So there are some tricks which are hidden everywhere, so I apologize for. I'll try to make it understandable.
Another question? No? Okay, so let's thank the speaker again.